Good afternoon. Yes, indeed, I'm from the same department as Vladimir Petrovich Gert, and I just noticed this morning that I have 18 slides, and I just remembered that he always said that the presentation should be no longer than 18 minutes. So Vagan Abgaryan and me will try to do like he said, well, something close to 18 minutes. So the title of the presentation is on stratification of state space by orbit types and hierarchy of classicality indicators. The presentation will be resembling the previous presentation. I mean the formulas and maybe some ideas, but I will try to to emphasize the results. So I will give some introduction on stratified structure of the quantum state space Pn. Then I will speak a bit about the Wigner function. Then we'll give some definitions of the orbit space, and finally move to the notion of the global indicator of classicality, and we'll exemplify that theory, that big theory, with an example of a three-level system, a Q-trig. So let's move forward. So on this slide you can see the main notions that I will use today. These are the following. We work on the quantum state space Pn. The elements of that space are Hermitian and non-negative and have a trace and are not normalized by 1. And also this, the dual space P asterisk, the elements of which are again Hermitian and possess the following equalities called the master equations, which were presented in the previous presentation. Those master equations were well, they okay, never mind. So the density matrix ρ is from the quantum state space Pn, and the Stratanovich-Weyl kernel delta is from the dual space P asterisk, and their combination, the trace of their product, is the Wigner function. So the Wigner function possesses some properties of classical statistical distribution, but also for some states it has negative values. So for us it's kind of an indication of some quantumness, and so we take that property as a basis for some investigation of quantumness. And for those purposes we introduced the so-called global indicator of classicality, which is defined as follows. We consider the orbit space of the state space where the Wigner function is positive, and calculate the relative volume. The motivation for this investigation is the following. Well, due to uncertainty principle, we cannot define whether the particle has the momentum P and position Q, and so one needs some quasi-probability distribution functions like the Wigner function or others that some kind of resemble the phase space distribution, and so we can fix some connections between the classical and the quantum statistical theory. So the Wigner was the first who introduced such kind of distribution function, which is now called the Wigner function or the Wigner quasi-probability distribution, and that sets some interrelations between classical and quantum mechanics. We define the quantum state space as the following. Pn, I already said about that, but again I will say that the elements are Hermitian, non-negative and normalized, and the unitary UN automorphism of the Hilbert space induces the joint SUN action on the state space, and that sets some equivalence relations between elements of Pn, and so due to that we can decompose over the strata in this way. So the Wigner function is is a trace of the product of the density matrix and the Stratanovich-Weyl kernel. They are presented here in the so-called block form, where psi is n squared minus one dimensional block vector. Lambdas are SUN algebra generators, and the Stratanovich-Weyl kernel is also presented in this form, where the summation is over the Cartan subalgebra elements, lambdas, and real coefficients mu live on one-dimensional sphere, and parameters nu label the members of the Wigner function family. So the Stratanovich-Weyl kernel is a mapping between the phase space and the dual space P asterisk, and supposing that that its eigenvalues are real and have the multiplicity, algebraic multiplicity ki, which means that the isotropy group of the Stratanovich-Weyl kernel can be written in this form. One can fix the, or no, not fix, but realize the phase space as a complex flag manifold, where these is the sequence of positive integers with some n, and so the family of the Wigner functions may be presented in this form. And from here we can see that if we put a restriction on the Wigner function so that it should be non-negative, we would get these restrictions on the block vector. So there is always a region inside the ball of the radius r asterisk, inside of which the Wigner function will be always positive. Here some definitions are given. So the unitary orbit space is a quotient space under the equivalence relation imposed by the adjoint SUN group action on the state space P. The set omega plus is a subspace where the Wigner functions are non-negative, knowing that the eigenvalues of the density matrix R and the eigenvalues of the Stratanovich-Weyl kernel delta are ordered in some chosen way, well, we choose this way, this decreasing order, we can define the orbit space OP as the following. It's defined as an ordered simplex n-1, and the subspace where the Wigner function is positive is then maybe defined by this dual con, where the eigenvalues of the density matrix and the Stratanovich-Weyl kernel are composed in this particular way. So the Wigner function is bounded by these expressions, and we're interested in the lower bound, where the Wigner function may be whether positive or negative, because the upper bound is always positive, so that always gives us a positive answer. So remembering the purpose of this work is that we should calculate the global indicator of classicality, so we should measure the portion of the positive states, and for that one needs to define a measure on the space and also to see to fix the domain of positivity of the Wigner function. So here are the expressions for the global indicator of classicality for a general case, and also for a degenerate case where we should see where we should calculate the global indicator on every orbit. So the state space is endowed with some Riemannian metric, GF, and dp is the corresponding measure. I will consider three of them, the Hilbert-Schmidt measure, and also two monotone, Buresh and Bogolyubov-Kubomori metrics. I will exemplify that theory by considering a three-level system, a Q-tree, the density matrix of which is presented on the slide, and the kernel is also presented on the slide. So we could define the orbit space of a Q-tree and its subspace of positive Wigner function in this way. And so for a Q-tree there are three classes of stratum. The first one is with dimension 6. It's a general case when none of the eigenvalues equals each other. The second class is when the dimension of the stratum equals 4. It's a case when two eigenvalues of 3 equal each other. And the third one, well, where all three eigenvalues equal each other, and that corresponds to a maximally mixed state, and the dimension of it is 0. So the stratas are colored by brown and blue line, segments. The brown segment corresponds to the strata O1 equals 2. 1 equals 2, but not 3. Well, vice versa. I'm sorry. 1 not equal 2 but equals 3, and blue wine to the other one. So the purpose is to calculate the volume of these regions. A lot has been said about the Hilbert-Schmidt metric today, so I will just say that the Hilbert-Schmidt distance between two infinitesimally close points defines the distance in this way. And for making use of the diagonal form of the density matrix ρ, we can rewrite the distance in this form. And since we have normalized eigenvalues of the density matrix, we could consider the one of the eigenvalues as a dependent one, and so get the explicit expression for the Hilbert-Schmidt volume element for general case and also for degenerate cases. So the first formula is a known one, and the second is NU1. And so calculating it, we get some results for the maximal stratum of Q indicator and also non-maximal stratum for two degenerate cases where the dimension was 4. And we see the plots for the general case, which is plotted as dot-dashed line, and also for the expression with some factor, I won't read it, where the blue curve is now the sum of the non-maximal Q indicators. I will give some explanation of that in the end. And so the final run is to consider also two monotone metrics, the Buresh, Wasserstein, and Bogolyubov-Kubomori metrics. and for them, the same calculations are the following. I didn't write the explicit expressions because they're a bit more complicated, but you can see the plots for, again, the general cases for the Buras metric on the left and Bogolyubov-Kubomori on the right, which were calculated yet numerically, and also the solid curves are the plots for the sums of numerators of the degenerate indicators over the denominators, sum of denominators. So the explanation is the following. Firstly, the global indicator is sensitive to two features. It's the negativity of the Wigner function and also some geometry that you choose according to your physical, according to your physics. I mean, you choose the measure that you want for solving some physical problem. And the second explanation is that if you want to recover the symmetry of the global indicator, you should consider not just the global indicator for some orbit, but to take the unification of that. So you should consider, you should unify the orbits by the same dimension. Yeah, thank you for attention.
Thank you very much. Astghik, very interesting your talk. With questions? This is our middle talk in this little three portion of our conference in quantum mechanics, and my interest is the stage when your research come to a point when you can give us a big matrix, numerical matrix, and try to develop the development of this indeed material. It will be my question is next, where you came to this come to this point when you took the numerical matrix for us.
Sorry, again?
This is interesting theory, and each physical theory came to a point when the theory we can apply. How we can apply? We must to construct Hamiltonian matrix and what is dynamic? Dynamic is a single-value decomposition. We must Schrödinger equations and obtain solutions. If you have a real matrix, we can do something. My question: in what time we can wait from you this point?
Maybe next year.
Next, oh, thank you very much.
Maybe I'll give some comment to this question. Gena, the subject of report not the dynamics systems like in mechanics and even quantum mechanics system, but actually the actual application of this technique is quantum information theory. It is classification of states of quantum systems.
Exactly.
So we don't the main application is quantum computing, actually.
Yes, yes. Okay. Thank you. Thank you. Thank you.
Thank you.
This next speaker once more.